Okay, shall we start? So this is the discussion for this week. We'll do some problems as usual. So problem number one. Let f be defined for all real x. Okay, and suppose that fx minus fy is less than or equal to x minus y squared for all x, y in R. Prove that f is constant. Okay, so proof. So what do we do? So one thing, we can divide both sides by x minus y. Okay. So on the left-hand side, that's just that. Okay, and we have this inequality, and then you take limit as x goes to y. Then this is going to 0, and this, the thing on the left-hand side, is nothing but derivative at y. Now, y is arbitrary, so the derivative of the function f is 0 everywhere, so that shows f is a constant. Okay, so that's number one. Number two. Okay, suppose f prime of x is greater than 0 in the interval ab. Prove that f is strictly increasing in AB. And let G be its inverse. Prove that. So the inverse function. Okay, so G is F inverse. Okay, so prove that G is differentiable and that its derivative G prime f of x is equal to 1 over f prime of x. Okay. So how do we do this? So let's do the first part first. That is, f is increasing. So, okay, so take any c and d with a less than c, or a less than c, less than d, and less than b. So what do we want to show is, we want to show f of d is greater than f of c. Okay, so f of d minus f of c is equal to f prime of some point p times d minus c, where p is between d and c, right? This is the mean value theorem. Okay, so f prime is positive, so that implies this is positive, right? So this is positive, so f of d is greater than f of c. So that shows our function is increasing. So in particular, f is 1 to 1, right? So if your function is increasing, it has to be 1 to 1. Okay, then use theorem 4.17, we know that G, being the inverse of F, is continuous. Okay. So how do we know G is continuous? Well, because F is differentiable, so F is automatically continuous, and then you just apply this theorem. Okay. All right. So what's next? Let me erase this. So if f of x is equal to y and f of x plus h is equal to, say, y plus k, then we have g of y plus k minus g of y over k less than 1 over f prime of x is equal to 1 over, say, fx plus h minus f of x over h minus 1 over f prime of x. Okay, so first observe that so f x plus h minus f of x, by definition, this is equal to k, right? So h here is g y plus k minus g of y. Okay, so why do we do this? Well, this looks like the derivative of g, right? So this is like the derivative of g, and that's if we can show that the difference has absolute value less than some epsilon, then g prime of y is very close to 1 over f prime of x, and x and y have this relation. Okay. All right, but now let's look at this. So that's look like that is like f prime of x, right? So in fact, the limit of, say, 1 over phi of t is equal to 1 over limit phi of t, provided that limit phi of t not equal to 0, right? So we take limit, all right? So because we know f prime of x is strictly positive, so this is not equal to 0, so we can move the limit over here. Then you know, if h is small enough, if h is small, then absolute value of 1 over fx plus h minus f of x over h minus 1 over f prime of x. So this can be very, very small. Okay, so that's that. Okay, next problem. Suppose g is a real function on R with bounded derivative. So g prime of x, absolute value, is bounded by some fixed number m, and fix epsilon greater than 0, and define f of x equals to x plus epsilon times gx. Prove that f is 1 to 1 if epsilon is small enough. Okay, so as the previous problem, we showed that, well, if the derivative of f is, say, always positive, then f is monotone increasing. a monotone increasing function is 1 to 1, right? So we just have to find an epsilon to make sure that the derivative of f is always positive. So how do we choose that epsilon? Well, if, say, epsilon is between 0 and 1 over m, then f prime of x is greater than or equal to 1 minus epsilon m, right? So that's greater than 1 minus 1, that's 0. Okay, so with this choice of epsilon, f prime is positive, so f is increasing, therefore monotone. Okay, so next, if, say, C0 plus C1 over 2 plus all the way to Cn minus 1 over n plus Cn over n minus 1 is equal to 0, where all the Ci's, so C0, C1, all the way up to Cn are all real numbers, prove that the equation C0 plus C1x plus all the way to Cn minus 1 xn minus 1 plus Cn x to the n is equal to 0 has at least one real root between 0 and 1. Okay. So how do we do that? So proof. Let's consider this polynomial. Consider p of x equals to c0x plus c1 over 2x squared plus all the way up to cn minus 1 over n x to the n plus cn n plus 1 x n plus 1. Okay, so basically here we put x and x squared and all the way to x n plus 1. Okay, so you know that if x is equal to 1, then it's just that, right? Okay, so note p of 1 is equal to 0, because p of 1 is just that. Okay, so what's the derivative of this function? So the derivative is what? C0 plus C1x plus all the way to Cn minus 1 x to the n minus 1 plus Cn x to the n. All right, so that's that. Okay, so essentially you want to show that the derivative of this polynomial is equal to 0 somewhere. Okay. Now, p1 is equal to 0. What about p0? If you plug in x equal to 0, that's also equal to 0, right? So by so what do we have over here? So p of 1 minus p of 0 is equal to p prime of, say, t times 1 minus 0, right? That's the mean value theorem. So this is equal to 0, this is equal to 0, so this is 0. This is 1, so this has to be 0, right? So by mean value theorem, this t is between 0 and 1. Okay, so there must be some t such that this is equal to 0. Okay. Next, suppose f is defined and differentiable for every x greater than 0, and f prime of x goes to 0 as x goes to infinity. So let's put g of x equals to f of x plus 1 minus f of x. Prove that g of x goes to 0 as x goes to infinity. Okay, so intuitively, g of x is, well, f of x plus 1 minus f of x. So basically, g of x is how much f increases if your input has changed by 1. And we also know that the derivative goes to 0. So if x is really, really big, then the rate of change is really, really small. So intuitively, if x is really big, f of x plus 1 and f of x, they should not differ by much. Okay, that is to say g of x goes to 0. Okay, so how do we prove that rigorously? Prove let epsilon greater than 0. So we can choose x0 such that for all x greater than x0, f prime of x is less than epsilon. Right? Such x0 exists because of that. Okay, so then again, by the mean value theorem, for any x greater than or equal to x0, there exists x1 in this interval such that f of x plus 1 minus f of x is equal to f prime of x1. So x1 is between these two, right? And x plus 1 minus x. Right? Again, this is the mean value theorem, but this is just 1. Okay, so the difference is equal to f prime of x1, but we know f prime of x1, the absolute value is less than epsilon, so that is less than epsilon, right? So that is to say g of x goes to 0. Okay. All right. Next. Next, let's say, suppose f is continuous for x greater than or equal to 0. So that's condition A. And B, the prime of x exists for x greater than 0. C, f of 0 is equal to 0. D, f prime is monotonically increasing. And let's put g of x equals to f of x over x. Okay, so x greater than 0. Prove that g is monotone increasing. Okay. Okay. So how do we show that g is monotone increasing? So it's same to show that, so I want to show g prime of x is greater than 0. Okay, and if we can show this, then G is monotonically increasing. So what is G prime of X? So if you use the quotient rule here, G prime of X is X times F prime of X minus Fx over X squared. So the denominator is always positive, right? So if you want to show this to be positive, then you really want to show X times F prime of X minus F of X is greater than 0. Okay. So how do we do that? Well, what conditions do we have? We have G prime of X exists, and F0 is equal to 0, and F prime is monotonically increasing. Okay, so F of X, because F0 is equal to 0, right? So F of X is equal to F of X minus F0. But this, by the mean value theorem, is equal to F prime of C times X minus 0, right? And C is between X and 0. All right, so that is to say F of X is equal to F prime of C times X. Okay, now C is between 0 and X, and we know F prime is monotonically increasing. So we have F prime of X is greater than F prime of C, right? So F of X is less than or equal to, or in fact is strictly less than, because it's monotone increasing. Okay, so Fx is less than F prime of X times X, and that is equivalent as saying the numerator is greater than 0. Okay, so G prime is greater than 0, so G is monotonically increasing. Okay, all right. Next. Okay. So next, basically L'Hopital's rule. So suppose F prime of X and G prime of X exist, and G prime of X not equal to 0, F of X equals to G of X is equal to 0, prove that limit as t goes to x, F of t over G of t is equal to F prime of X over G prime of X. Okay? So, how do we do that? Well, limit as t goes to x, F of t over G of t, that's equal to limit as t goes to x. Now, F of x is equal to 0, right? So I replace F of t by F of t minus F of x. It doesn't change anything, right? Because that's 0. And for the denominator, same story. I subtract G of x. Nothing's going to change. So this is equality, right? So these two are the same. Now if I divide t minus x for the numerator and the denominator, again, same operations on both, so it doesn't change. Okay? So now, because the limit exists, so when you're evaluating this limit, you can evaluate the limit of numerator and denominator separately and then divide them. So that is to say, limit of f over g is the limit of f over limit of g, provided that the limit of g is not equal to 0, right, which is given. So really, that's ft minus fx over t minus x over limit g of t minus g of x over t minus x. But this is nothing but the derivative of f at x, right? So that's f prime of x, and the denominator is g prime of x. Okay, so we have proven the L'Hopital's rule. Okay. All right, next. Let f be a continuous real function on R, and we know that f prime of x exists for all x not equal to 0, and that f prime of x goes to 3 as x goes to 0. So does it follow that f prime of 0 exists? Okay, so first of all, what is f prime of 0? So that's limit f of t minus f of 0 over t minus 0 as t goes to 0, right? That's the definition of f prime of 0. Okay. So, how do we know if that exists? Well, first observe that as t goes to 0, both the numerator and denominator goes to 0, right? The numerator goes to 0 because f is continuous, so you can use L'Hopital, right? Use L'Hopital, so that's the limit as t goes to 0. F prime, well, by L'Hopital, this is f prime of 0 over 1, right? Derivative of t is 1. Well, okay. I should say this. So that's the limit as t goes to 0, f prime of t, right? Over 1. Okay, now because of that, we know this is equal to 3. Okay, so f prime of 0 is equal to 3. The limit exists. Okay. All right, next. Suppose f is defined in a neighborhood of x, and suppose f double prime of x exists, show that limit as h goes to 0, f of x plus h plus f of x minus h minus 2 f of x over h squared is equal to the second derivative of f at x. Okay, so what do we do here? So if you look at the left-hand side, as h goes to 0, because f double prime exists, so that means f prime exists and is continuous, and that in turn implies f is continuous. Okay, so as h goes to 0, by the continuity, you know the denominator is going to 0. So is the numerator denominator, they both goes to 0. Okay, so essentially that's a 0 over 0 problem. Okay, so what do we do then if we have 0 over 0? Well, we use L'Hopital. Use L'Hopital. So you take the derivative of the denominator, you got 2h. Derivative of the numerator, you have what? So you have f prime x plus h minus f prime of x plus h, x minus h, right? And that's it. Because here, remember, h is changing, right? H is going to 0. So when you take derivative, you are taking derivative with respect to h, right? And this 2fx, this has nothing to do with h. So if you take the derivative of this with respect to h, you get 0. So that's why we don't have additional term over here. Okay, so that's that. Okay, so this is equal to what? So here's a 2 there, we can take it out. So that's 1 over 2, right? And then we're going to do this usual trick because we want to get the second derivative. So what do? So we subtract this f prime of x and add it back. Okay, that's the limit of sum, so it's equal to the limit of this plus the limit of that. And as you can see, as h goes to 0, this is going to f double prime of x, because that's, you think of f prime as the function, right? So it's derivative of this function f prime, so that's f double prime. So same story here, that's f double prime, right? Because the 1/2 in the front, you have f double prime of x. Okay, so so here some of you might wonder, because we take derivative with respect to h, so this thing really has nothing to do with this expression, right? It has nothing to do with that, nothing to do with that. So does that imply if we replace this by anything else, as long as it's independent of h, we'll get the limit equals to f double prime of x? Well, that sounds strange, and in fact, that's not true, because we need this 2fx so that as h goes to 0, the numerator goes to 0. So then we can apply L'Hopital's rule, right? Otherwise, if your denominator is going to 0, but numerator is not going to 0, you simply have plus or minus infinity. Okay, so you can't use L'Hopital's rule there. Okay, next, assume f from R to R is differentiable. So part A, if there exists L less than 1, such that for each x in R, we have f prime of x less than L, prove that there exists a unique x such that f of x is equal to x. Okay, so let's do part A first. Okay, so what do we do? So what's the intuition behind this? Say, so let's think f of x, say f of x minus f of y. Let's look at their difference. So by the mean value theorem, you know that this is less than L times x minus y, right? With L being less than 1. So the length of this is less than the length of that. Okay? So you have an interval. If you map it, so say this is x, this is y, right? So the image, we know it's again an interval. So this interval is smaller, right? Okay, so you can think of this function as a sort of contraction map. So that means it's contracting this interval, the length. Okay, so if a map is contraction, so it can only shrink this interval, right? So eventually you're gonna shrink to a point. Okay, so that's the intuition. So how do we prove that rigorously? So take any x0 in R. If f of x is equal to x0, if f of x0 is equal to x0, then we are done. Right, because we found a fixed point. So if not, say suppose f of x0 is greater than x0, then by the mean value theorem, for each t greater than x0, there exists, say, a theta on this interval with f of t is equal to f of x0 plus f prime of theta times t minus x0. Okay, so we know this is less than f of x 0 plus L times t minus x0. Okay, so if we take t greater than f of x0 minus x0 over 1 minus L, then we get that f of t is less than f of x0 plus L t minus x0. So you're plugging this into here, right? Okay, so it's going to be less than, t. Right? Okay. All right, so we have f of t is less than t. Okay, so now you look at this function f of x minus x. So because f of x0 is greater than x0, so this is positive at x0, and at t, so f of t minus t, that's going to be negative, right? So this continuous function is positive at one point and negative at the other. So you know it will cross the x-axis somewhere, right? And when the crossing happens, that means f of x is equal to x. So you have a have a fixed point. Okay. All right. So it is also possible that f of x0 is less than x0, but the logic's the same. So I will leave that as a exercise. Okay. So how about uniqueness? So we haven't proved the uniqueness, right? The uniqueness is almost immediate. Say you have f of x is equal to x and f of y equals to y. Then f of x minus f of y absolute value less than L x minus y with L less than 1 cannot happen, right? Because this is equal to that. So this can only happen if x minus y absolute value is equal to 0, right? And that means x is equal to y. So the fixed point is indeed unique. Okay, so that's that. So here's a crucial assumption is that L is less than 1. So if we relax the condition, so show by example that part A fails if L is equal to 1. Okay. So that means if f prime of x is less than 1, then it might not be true that f has a fixed point. Okay. So let's take, say, f of x equals to x plus e to the minus x. Then f prime of x is equal to 1 minus e to the minus x. And we know that's strictly less than 1, but there does not exist an x such that f of x equals to x, because that will imply x plus e to the minus x equal to x. And that's impossible because this is always strictly greater than 0. Okay, next problem. So suppose f from a to b to r is monotone increasing, and part A, let x be a point on the interval, and alpha sub x is equal to the supremum of f of t with t less than x. Show that the left limit, so it's the limit as t goes to x from the left, f of x is equal to alpha sub x. Okay, so what do we do? Oh, this looks very intuitive, right? Alpha x is defined to be the supremum. So if t is very close to x from the left, then because our function is monotone increasing, so naturally the limit should be the supremum, right? So it's a monotone increasing function. Say this is x, right? So you approach x from the left, should be the supremum, right? So the supremum is right here. Okay, how do we show that rigorously? So prove let epsilon greater than 0. Then we know by definition of supremum, this is not a upper bound for the set f of t with t less than x. So there exists t less than x with alpha minus x, alpha sub x minus epsilon less than f of t less than or equal to alpha sub x. Okay, since f is increasing, so for all s on the interval from t to x, we have alpha x minus epsilon is less than ft, less than or equal to f of s, and less than or equal to alpha x, right? So fs minus alpha x is less than epsilon. So since epsilon is arbitrary, it follows that the left limit is alpha sub x. Okay, so next part B. So we similarly define the right limit. So I'm going to use the shorthand. So this is the left limit of f approaching x from the left. So this is the right limit. Say if that is true, and let I sub x be the interval. So fx minus fx plus. Okay, so ix, call it the jumped interval. Okay, so call ix the jumped interval at x. Show that if ix and ix prime are jumped intervals at 2 points, at x and x prime, let's say x is less than x prime, then the two jumped intervals are mutually exclusive. Okay, so what does that mean? Well, so this can only happen if your function is discontinuous at this x, right? So this is the right limit, that's the left limit. Okay, so ix is just this interval. Okay, suppose we have another jump, say over here, then that's the jumped interval. So as you can see, these two intervals are disjoint. Okay, so how do we rigorously show that? So let t be a point in x and x prime. Okay, so t is somewhere over here. So since f is increasing, so f is increasing, so using a, okay, you can similarly show that this would be the infimum of f of s with s greater than x, right? So the function is increasing, so the right limit is equal to the infimum, right? Okay, good. So this is less than or equal to f of t by definition, because t is greater than x. Okay, so similarly, f of t is less than or equal to the supremum of f of s with s less than x prime, right? So this is f of x prime minus. Okay, so therefore, So f of t is greater than this but less than this. So you know that f of x plus is less than or equal to f x prime minus, okay? So you have two intervals, right? The right endpoint is less than the left endpoint of that. So they are disjoint. Okay, so that's that. That's so much for today. So if you have any questions, please ask during discussion. See you next time.